427 days into what should have been a simple 30-day mission, the situation has transformed into a quiet crisis unfolding millions of kilometers from Earth. On the surface of Mars, 297 million kilometers away, a tiny helicopter named Ingenuity is struggling for survival. This isn't just any robotic explorer, it's a marvel of engineering, weighing just 680 grams and built with off-the-shelf components. Some parts came from an Android smartphone, others from a cordless drill. What started as a modest technology demonstration has now become one of the most remarkable stories of space exploration. Ingenuity had already far exceeded expectations. But something is going wrong. The Martian winter is creeping in, and with it comes darkness and deadly cold. Each night, the temperature on the red planet plummets to a chilling -85 degrees Celsius. As Mars moves further from the Sun, not only does it get colder, but the atmosphere becomes increasingly hostile. Dust storms stir up with growing ferocity, obscuring the Sun and making it nearly impossible for solar-powered machines like Ingenuity to recharge. On her 427th Martian day, known as a SOL, Mission Control at NASA's Jet Propulsion Laboratory in Southern California attempts to contact her, just like every day before. But this time there is silence. They try again. Nothing. The signals that once beamed so reliably from the Martian surface are gone. For the team on Earth, the signs are grim. After everything Ingenuity has achieved, it seems the mission might finally be over. But there's still one final method left to try. One last trick that might reconnect them with their mechanical pioneer. To understand why this moment is so significant, we need to go back to the beginning. Ingenuity was a gamble. 6 years earlier, a team of scientists and engineers were piecing together what many at NASA considered a risky experiment. Kenneth Farley, the project scientist for the Mars 2020 Perseverance mission, openly admitted, "I've personally been opposed to it." The argument was that a 30-day tech demo didn't align with NASA's core scientific goals. In short, many believed it was a distraction. Unlike billion-dollar Mars missions, Ingenuity had a lean budget of just $80 million, less than the cost of the Hollywood film, The Martian. But the team was determined to prove that controlled flight on another planet was possible. They designed a helicopter that was ultralight, with blades that spin at over 2,400 revolutions per minute, necessary to lift in Mars' thin atmosphere, which is only 1% as dense as Earth's. On February 18, 2021, NASA's Perseverance rover touched down in Jezero crater. Attached beneath the rover was Ingenuity, cradled carefully during entry, descent, and landing. This was Sol 0, the first day of Ingenuity's life on Mars. Soon after, the rover deployed the helicopter onto the surface, severing its connections. From that point on, Ingenuity was on her own. Her mission was simple: fly once, maybe twice, and prove it could be done. No one really expected more. Over the next 2 months, NASA ran rigorous checks on Ingenuity's systems. They spun her blades, tested her navigation, and checked her flight computer. On Sol 58 she was ready. Her blades spun up, she rose into the air, and for the first time in history, something human-made flew on another world. It happened just 120 years after the Wright brothers' flight on Earth. Within a few days she flew again. Then again. And again. Within a month, Ingenuity had completed 5 successful flights. Her original mission was finished. She had done the impossible. But with success came new expectations. NASA decided to extend her mission. Now, Ingenuity would assist the Perseverance rover by scouting ahead and exploring dangerous or unreachable terrain. It was a huge honor, and a huge challenge. The original 30-day tech demo suddenly became an open-ended mission. The team had no roadmap for this. They had planned every previous flight meticulously, using satellite data and rover imaging to prepare for months. But now they were chasing a moving target. Ingenuity had to keep up with Perseverance and adapt on the fly, literally. Complicating things further was the delay in communication. Mars is at least 56 million kilometers from Earth. Even when it's at its closest, there's a minimum 6-minute round-trip delay for any signal. That's far longer than Ingenuity's maximum flight time of 2 minutes. So, every flight must be pre-programmed. Ingenuity has to fly completely autonomously. To do that, she relies on her 2 onboard cameras. A 13-megapixel forward-facing color camera for scouting, and a downward-facing black and white camera used for navigation. This navigation system works a lot like an optical mouse. The camera continuously takes 30 images per second, analyzing how rocks and terrain features move beneath her to track her position. But it's not foolproof. On Flight 6, Ingenuity left her well-mapped test area for the first time. About 54 seconds into the flight, she began to wobble violently, tilting up to 20 degrees. Alarms went off. What had happened? It turns out, a rare overlap in the timing of camera images caused a miscalculation. The system received a color image at the exact same moment as a navigation image. That caused the computer to drop one of the black and white frames, throwing off her internal sense of position. She thought she was lagging behind, so she overcompensated, then overcorrected, creating a dangerous wobble. Fortunately, the software detected the instability and initiated an emergency landing. Back on Earth, engineers diagnosed the problem and issued a software patch. Ingenuity was bruised but not broken. She flew again. And again. And she kept up with perseverance across Martian plains. Then came Flight 19. Just before liftoff, the team received an alert. A dust storm was brewing near Jezero crater. They canceled the flight and waited. The storm hit hard. For 6 days, violent gusts of dust up to 20 meters per second battered the region. But when the skies cleared and contact was restored, Ginny was still standing. She had survived. However, the storm left behind two major issues. First, dust had coated her solar panels, reducing power generation by 18%. Second, that fine Martian dust had jammed her servos, the mechanical joints used to tilt her rotor blades. When they tried to prepare for Flight 19, the servos wouldn't budge. JPL engineers had anticipated these problems, but with a limited budget and time, they hadn't implemented full solutions. Instead, they improvised. To fix the servos, they simply wiggled them repeatedly until the dust cleared. It worked. Ingenuity could fly again, although with shorter flights and more caution. But the environment wasn't going to get any easier. As winter on Mars deepened, temperatures dropped even further. Every night, the helicopter had to rely on its internal battery-powered heater to stay warm enough to function. Mars doesn't make things easy. Its freezing nights, deadly dust, and thin air present a nightmare scenario for any machine. Ingenuity wasn't designed for long-term survival in these conditions. But she kept going. Every flight was a victory. Every successful mission another testament to the ingenuity of the team that built her. Now, back at Sol 427 with no signal coming through, the team stares at their monitors in silence. The odds aren't good. The winter might have finally claimed their helicopter. But they have one final strategy. A carefully timed, high-powered signal is sent to trigger a system reboot. If she's still alive, it just might work. This tiny machine, built with consumer parts and a modest budget, has flown more than 30 times over alien terrain. She's traveled more than 10 kilometers and climbed to heights over 10 meters, all while sending back priceless data. She is not just a test subject anymore, she's a Martian explorer. What began as a side project has redefined the future of space exploration. Ingenuity has paved the way for future aerial missions on Mars and beyond. Her legacy will live on in every drone that follows her, in every scout that flies where no rover can go. And whether this final signal brings her back online or not, Ginny has already made history. She wasn't supposed to last. She wasn't supposed to explore. But she did. And now the world watches and waits, hoping for one more flight. See, every Martian night, the temperature drops precipitously. My friend Alex from the channel Astrum explains it perfectly. With such a thin atmosphere, Mars is terrible at holding on to heat. Once the sun sets and the surface starts to cool, there's virtually no air to trap the heat, so it escapes almost instantly. The result? Drastic, bone-chilling temperature swings. For example, if you stood on Mars during the warmest part of the day near the equator, your feet might feel a comfortable 23 degrees Celsius. But by the time you looked up, your head could be facing a chill of 0 degrees Celsius. This kind of extreme vertical temperature difference is unheard of on Earth, and it's just the beginning. Between day and night, Mars can swing from around 27 degrees Celsius to an absolutely freezing minus 133 degrees Celsius. It's not just uncomfortable, it's dangerous for delicate electronics. If you're interested in the planet's climate and how these wild shifts contribute to massive dust storms that can cover the entire surface, check out Astrum's deep dive into the Martian climate. These storms are no joke. They can last for weeks and block out sunlight, starving solar-powered tech like Ingenuity. As Ginny's mission continued, Mars drifted farther from the sun, sliding into its winter phase. And that brought even colder nights. Now here's the catch. Many of Ginny's essential components are hand-soldered. Those wild temperature shifts cause the metal in the solder to expand and contract repeatedly. Over time, this stresses the connections and can eventually cause them to crack or break. Then there's the battery issue. Inside the batteries, A liquid electrolyte solution helps lithium ions move back and forth. But if that liquid freezes, the battery stops working completely. That's mission over. To keep that from happening, engineers at JPL housed all the sensitive parts in a warm box. It includes resistance heaters that turn on during the Martian night. It's not a luxury. It's a necessity. Here's how the battery usage breaks down. Only about 25 to 30% of the power goes to flying. The other 60 to 75%? That's just spent staying warm overnight. But here's where it gets tricky. The colder it gets, the harder those heaters have to work. And when they struggle, the battery gets colder and produces even less power. It's a vicious cycle, a death spiral that could bring the mission to an end. Then came the wake-up call. On the morning of May 3rd, the team at JPL went about their routine. They checked the latest data download from Ingenuity. Nothing. They pinged the helicopter. Still nothing. Silence. Had they finally lost her? Was this the end of the $70 million experiment? Everyone held their breath. No one wanted to say it out loud, but the question hung in the air: is the mission over? Instead of panicking, the team took a step back. They worked through every possible failure scenario. And one hypothesis stood out. Ingenuity is designed with a sort of alarm clock mechanism. Each morning it powers on and stays awake for 15 minutes. If it doesn't receive a signal during that time, it goes back to sleep, waiting for the next scheduled wake-up. But what if the batteries had completely drained during the night? If that happened, Ingenuity would power down entirely, including the clock. When the sun rose again, if her components were still intact, she might slowly recharge and wake up, but with a reset clock. So they ran the numbers. Given the current conditions and sunlight, they calculated that if Ginny was still functional, she should wake up at exactly 11:45 a.m. Martian time. That was a huge insight because up until then, the team had been trying to reach her at the wrong time. So they shifted the schedule and began sending signals around 11:45 a.m. ping after ping. They called out to her. And then she answered. She was alive. Next they assessed the damage. Most of Ginny's warmbox components were only rated to survive down to -45 degrees Celsius. She had experienced full-on Martian freezing. But miraculously almost everything had survived. Almost. One crucial component had died, the inclinometer. Now the inclinometer is essential. It tells the helicopter its exact orientation in three-dimensional space before it attempts flight. Without this, it can't know if it's tilted or how to correct its angle. Even a 10-degree misalignment could mean crashing into the ground or flying off course into a rock. So initially this seemed like a fatal blow. But then, someone had an idea. Ingenuity, after all, is made using smartphone components. Her processor? A Samsung Galaxy S5. Some of her sensors? Straight from a Google Pixel 3. And inside every smartphone are tools that mimic what the inclinometer does. These are microelectromechanical systems, or MEMS, including accelerometers. These devices contain a tiny mass suspended by flexible arms. When the device accelerates or tilts, the mass moves. This change alters the capacitance between the mass and nearby plates, which can be measured and translated into acceleration. Hooke's law explains the relationship between force and displacement in the springs holding the mass. F equals kx. Combine that with Newton's second law, F equals ma, and you get A equals kx/m. Since acceleration is linked to displacement, and capacitance varies with that movement, we can track changes accurately. And when you integrate acceleration over time, you get velocity and position. Add gyroscopes to the mix, and you get an inertial measurement unit, or IMU. Guess what? Ingenuity already has an IMU, the same one used in the Google Pixel 3. So the team thought, why not reprogram Ingenuity to use the IMU instead of the inclinometer? After all, the inclinometer is essentially just accelerometers that give roll and pitch data before takeoff. And the IMU does exactly that plus more. With some clever software work they pulled it off. They bypassed the dead inclinometer and brought Ginny back to life. If they had lost almost any other component, this might not have worked. But they got lucky. The one instrument that died was the only one they could afford to lose. But luck only goes so far. There's another looming threat: cosmic rays. See, none of Ingenuity's parts are space-grade. They were never meant to survive years on another planet. That means they're especially vulnerable to cosmic radiation. Unlike Earth, Mars has almost no magnetic field and a paper-thin atmosphere. That allows cosmic rays to slam into the surface and even penetrate electronics. A single cosmic ray can flip a bit in a computer's memory. That bit flip might seem minor, but it can cause wild, unpredictable behavior. On Earth, It once added 4,096 phantom votes in a Belgian election. So how hasn't Ginny crashed by now? If you had asked NASA a decade ago whether you could run a Martian helicopter with a standard smartphone processor, they'd have said no. They would have predicted it would fail in just a few days. But reality has been far kinder. These commercial, off-the-shelf parts are performing way better than expected. In fact, it's led to a change in mindset at NASA. Instead of building custom radiation-hardened processors, it might be smarter to just buy commercial processors in bulk, put them through radiation tests and see which ones hold up best. This is a game changer. It drastically reduces development time and cost, and it opens the door for more flexible, powerful technology on future missions. Ginny survived the Martian winter thanks to these parts, though it was close. She stayed just within communication range of the Perseverance rover, and every day they stretched the limits. Every night was a gamble. But then, finally, spring arrived. The sun hung longer in the Martian sky. Solar panels gathered more energy. Batteries charged more fully. And Ingenuity was no longer just surviving, she was thriving again. The birds were chirping on the Martian surface. Well, not literally, of course. But there was this distinct feeling in the air, a kind of optimism that mirrored the arrival of spring. It was like coming out of a long Martian winter. With the increased sunlight beaming down, the little helicopter could now fully recharge its solar panels. This wasn't just a seasonal change, it was a new phase in the mission. Ingenuity was ready to return to work, not as an experiment anymore, but as a vital scout and scientific companion. The team was energized and so was Ginny. Over the course of the next 41 flights, Ingenuity would take on tasks that Perseverance simply couldn't. She soared above rocky terrains and ventured into zones the rover couldn't reach. Her mission was to image craters, map out terrain, and snap stunning visuals of the Martian horizon from above, something no one had ever done before on another planet. She wasn't just flying anymore, she was testing the limits of Martian aviation. The team began conducting daring aerodynamic experiments, pushing the envelope of what was thought possible. Each flight brought new records and new challenges. They wanted to fly faster. But with speed came new complications. The faster Ginny flew, the quicker the Martian surface features zipped across her camera's field of view. And that was a problem. Her navigation system depended entirely on those visual markers. It couldn't keep up. The solution? Ingeniously simple: fly higher. By gaining altitude, Ginny could expand her field of view. That way, even though she was going faster, the features on the ground moved more slowly across the frame, giving her time to react and adjust. So they started experimenting. From the original plan of flying at just 10 meters above the surface, they gradually increased that height to 24 meters. This gave Ginny the visual buffer she needed to push her speed limits. As a result, she went from cruising at just 2 meters per second to a whopping 10 meters per second. It was a game changer. Flight after flight, she shattered previous records: speed, altitude, distance. Everything they could possibly test, they did. This was a once-in-a-lifetime chance, and the JPL team made sure to squeeze out every bit of data and experience from having a helicopter on Mars. Everything was going well. Ingenuity and Perseverance had journeyed all the way to a fascinating location called Neretva Vallis, a dried-up river delta inside the Jezero crater. But then came Flight 71. And with it, a problem worse than anything Ginny had encountered before. See, Ingenuity only carries one scientific payload: a camera. But that single camera is everything. It takes hundreds of photos each day and beams them back to JPL. Perseverance does the same. There's even a photo of the two of them together, a Martian selfie. It's adorable and kind of poetic. In a way, Ginny and Perseverance are the most online duo on the entire planet of Mars. We always know where they are and what they're doing. They're constantly sharing snapshots of their journey, like two very active users on a cosmic social media platform. And if you think about it, that's not all that different from us humans. We live our lives online, constantly uploading our data. But the difference is our data doesn't sit quietly in a NASA archive. It's bought, sold, and used in ways most of us aren't even aware of. That's actually why I've been using today's sponsor, Incogni. I signed up a year ago, and since then, they've filed over 300 data removal requests on my behalf. That led to my information being deleted from over 100 marketing and spam databases. Doing that manually would have taken me over 230 hours, basically weeks of my life. That's time I'd rather spend making these videos. So if you want to take back control of your personal data, head to incognitoani.com/veritasium. I've also added the link in the description, or you can scan the QR code on screen. And make sure to use code VERITASIUM to get 60% off your annual subscription. Seriously, it's a smart move in this hyper-connected world. Once again, that's incognitoani.com/veritasium. Huge thanks to Incogni for sponsoring this part of the video. Now back to Ginny and her final flights. There was just one last challenge left. Ingenuity needed to cross a sand dune and reach a spot called Bright Angel to meet up with the rover. So on Flight 71 she took off. Things seemed fine at first, but about 10 seconds into the flight her navigation started failing. She went into emergency landing mode and came down hard. The team quickly pinged Ginny and she was still alive. Relief. But they needed to know what went wrong. When they reviewed the error codes, the answer became clear. As Ginny flew over the dunes, her camera couldn't find enough visual markers. No rocks, no strong contrast to track. Without those references, she couldn't figure out where she was in space, so her software triggered an emergency descent. It was similar to what had happened back in Flight 6. But this time there was no software patch that could fix the issue. The team checked her body for structural damage and surprisingly she seemed intact. So they tried again. A simple test flight, just go up, take some pictures and come back down. That was Flight 72. And that's when everything changed. As she climbed, everything seemed normal. But during the descent, the same navigation issue struck again. She lost track of her position. This time though, it was fatal. She came down hard. Perseverance rolled over to her location and captured a heartbreaking image of her wreckage. The blades were shattered. The moment the team saw that photo, they knew it was over. The feeling was gut-wrenching. This wasn't just a machine, it was a pioneer. And now the mission couldn't continue. It was devastating. But one question lingered. Why did Flight 71 end with only a hard landing while Flight 72 ended in disaster? Both flights had the same navigation problem. Both landed in roughly the same way. And yet, only one of them ended with broken rotors. The team at JPL needed answers. This wasn't just about a helicopter crash, it was about conducting the first ever air crash investigation on another planet. Think about that. The first aircraft to fly on another world, and now the first aircraft crash to be investigated off Earth. History was being made again. When they analyzed the crash site, they noticed something strange. The rotor blades were broken, yes, but not in the way you'd expect. Normally, when high-speed spinning blades hit the ground, they leave a telltale pattern. A spray of debris, a scarring of the terrain, something visible even from orbit. But this time there was no such pattern. It was like the blades broke without even touching the ground. That didn't make sense. So they pulled out a prototype blade from the original development phase, identical in construction to the ones Ginny used on Mars. It was made from carbon fiber composite with a foam core. Super light. So light, in fact, that when someone picked it up for the first time they were shocked. It felt like holding nothing at all. But still, these blades were strong. So how did they break? The answer lies in how forces act on spinning blades. When a helicopter blade spins, the tips trace a circle much like a hula hoop. If you apply a force upward on one side, you might expect the rotor to tilt immediately in that direction. But that's not what happens. Because the blades are moving fast, the force applied doesn't cause an immediate tilt. Instead, the effect shows up 90 degrees later in the rotation. It's a phenomenon called precession. You can see this effect in a spinning bike wheel, where pressure applied in one direction causes movement in another. Now, Ingenuity had two sets of blades spinning in opposite directions. So overall, the opposing torques canceled each other out, keeping the helicopter balanced. But that didn't stop each individual blade from flexing under stress. And that's where the real issue began. Because of precession, the blades experience stress at very specific points, right where the final reinforcement tapers off. If a blade were to break due to this force, it would snap exactly there. And that's precisely what the post-crash photos showed, a jagged tear right at the tip where the structure was weakest. So that's what happened. On Flight 72, Ginny came down at an angle, landed hard, and the force traveled through her frame. That created a precession torque, and the blades flexed and failed at their weakest point. The landing gear, avionics, servos, all intact. It was the rotors that gave way. That discovery is shaping the future. The next generation of Mars helicopters, known as Chopper, will have reinforced blades, specifically designed to handle that kind of stress. And you remember how light Ginny's blades were? Choppers are tougher but still lightweight. It's also got 6 rotors instead of just 2, and it can carry real scientific instruments. For the first time, we're looking at a helicopter that can be a fully independent science platform. Even the communication system has been upgraded. They've developed a lightweight radio that can talk directly to orbit. No more trailing Perseverance like a little sibling. Now, Chopper can explore wherever it wants, completely untethered. In fact, the design includes a modular science bay, about the size of a small blue box, that can hold up to 5 kilograms of instruments and tools. You could fly 3 kilometers per Martian day, covering terrain in minutes that would take a rover days or even weeks to traverse. The science community is buzzing with excitement. And this isn't some far-off dream. They've already built a 5th-scale model. It's made of 2 parts, the chopper platform itself and a mid-air delivery system. Because helicopters don't need sky cranes. The idea is this: descend through the atmosphere with a jetpack, slow down just enough to release chopper, and then let it take off mid-air and land under its own control. Just bold. It's elegant. And it's the beginning of a new era. Rockets ignite. Countdown hits 0. And chopper's future takes flight. One day there will be fleets of these helicopters zipping across Mars, flying through canyons, over volcanoes, even across icy poles. Airports on Mars? Absolutely. Bigger aircraft, smarter systems, wider exploration. All of that stems from one little helicopter that no one thought would work. Ingenuity changed everything. When she was first proposed, even NASA doubted she could fly. But she did. She proved what was possible. It's like the early 1900s. Back then, if you said you were going to fly, people thought you were a lunatic. Then the Wright brothers flew and suddenly, everything changed. And so, attached to the underside of Ingenuity is a small scrap of fabric. Just 1 square centimeter. It came from the original Wright flyer. From the first flight on Earth to the first flight on another world. That connection? That legacy? It's eternal. And though Ginny now rests on the surface of Mars, she's not entirely gone. She's still functioning. Still alive. Every day she wakes up, captures photos, takes temperature readings. She's a weather station now. A silent sentinel. A survivor. No one ever predicted this. No one expected that after her final flight, she'd still be contributing. She's a tank. And the team? They couldn't be prouder of her. From a tech demo to a legend. Ginny showed us that the sky isn't the limit, not even on another planet. Thanks for watching.